Where do you have the link on the YouTube channel?
It's on Blackboard. On the information about the course. If you go to YouTube, there is a channel called Nathanson Math Lectures, and then and there are various playlists, and one is for linear algebra for this semester. But all this information is on the course information sheet on Blackboard for this section of linear algebra. Okay, let's start. So what I'm talking about today is section 3C on matrices. And the connection between matrices and linear maps. So we have a vector space V and a vector space W, and T from V to W is linear. That means that for any two vectors, V1 and V2 in V, T of V1 plus V2 is T of V1 plus T of V2. And for any scalar and any vector V, C times V, T of a scalar times a vector is the scalar times T of the vector. That's the definition of linear. So suppose that V is finite dimensional. That means it has a finite number of elements in the basis. And the basis is the ordered sequence V1, V2 up to V sub n. So every vector V in the vector space V is a linear combination of the basis vectors C1, V1 plus C2, V2 up to C sub n, V sub n. And so T of the vector V, that's T of C1, V2, V1, C2, V2 up to Cn, Vn. But because T is linear, this is T of C1, V1 plus T of C2, V2, and so forth, up to C of Cn, Vn. That's using this property of a linear transformation. And using the scalar multiplication property, I can take the scalars outside. C1, T of V1 plus C2, T of V2 up to Cn, T of Vn. So T of V is the linear combination of the vectors T of V1, T of V2 up to T of Vn. Right, so this is just general information about a linear transformation. And but what this tells us is if we know how the linear map T acts on the basis vectors, that's all we need to know to understand how T acts or transforms any vector in the vector space. So suppose V has this basis, V1 up to Vn, and suppose W, which is another finite dimensional vector space, has a basis W1 up to W sub n. So for all k from 1 up to n, T of the basis vector Vk is some linear combination of W1 up to Wn. It's some, I can say, A1k W1 plus A2k W2 plus A MK WM. Right. T is a map from V to W. So for every basis vector, VK, T of VK is in W. That means it's a linear combination of these vectors. And so we use these scalars, A sub jk, so J goes from 1 to M, and K goes from 1 to N, to create a matrix, to form an M by N matrix A. And I write in the kth column, I write these scalars that you see that you obtain from T of VK. So this is A1K, A2K, down to AMK. There are M rows in this matrix. And there are N columns. So in the first column, column 1, to be A11, A21, down to AM1. And in the nth column, to be A1N, A2N, down to AMN. So I've associated to every linear map a matrix. And let's look at an example. Let me start with one of the examples that's in the text. So I have T, a linear map from F2 to F3. Remember, F is the field of real or complex numbers. So it could be R2 to R3 or C2 to C3. So T is going to be this linear map defined as follows. T of the vector XY, that's a two-dimensional vector, is going to have to be a vector with 3 coordinates because it's an F3. X plus 3y, 2x plus 5y, 7x plus 9y. Again, it's your choice whether to write vectors horizontally or vertically. Find the basis. With respect, find the matrix with respect to the standard basis. Just a moment. Here's the one. All right. Find the matrix with respect to the standard bases. So what are the standard bases? For F2, we have the vector E1, which is 1, 0, and E2, which is 0, 1. And for F3, the standard basis is E1 is 1, 0, 0. I'll call it F1. F2 is 0, 1, 0. And F3 is 0, 0, 1. So to find the matrix, we have to compute T of E1 and T of E2. So T of E1, this is T of the vector 1, 0. What is T of 1, 0? You let x equal 1 and y equals 0. When x is 1 and y is 0, you get 1, 2, 7. E2 is the vector 0, 1. When x is 0 and y is 1, you get 3, 5, 9. So the matrix M of t, this is the first column, 1, 2, 7, and this is the second column, 3, 5, 9. So this is the matrix for this linear map. Let's take another example. Suppose I take t, let's say from F3 to F3. So this is a linear map from three-dimensional space to three-dimensional space. And let's say t of x, y, z is x plus y plus z, x minus 2y minus 3z, y plus 5z. So this is a linear map. And how do we calculate its matrix? It's from a three-dimensional space to a three-dimensional space. So it's going to be a 3 by 3 matrix. We have to compute t of 1, 0, 0, t of 0, 1, 0, and t of 0, 0, 1. When x is 1 and y and z are 0, I get 1, 1, 0. So in my matrix, that's the first column, 1, 1, 0. T of 0, 1, 0, when y is 0 and the other coordinates are, when y is 1 and the other coordinates are 0, I get 1 minus 2, 1. So 1 minus 2, 1 is the second column. And when x and y are 0 and z is 1, I get 1 minus 3, 5. So what I've just done is associate a matrix to a linear map. Any questions about this? Okay. Let's look at a third example. Suppose P sub m is the set of all polynomials of degree at most m. So I can write every polynomial of degree at most m as c0 plus c1x plus c2x squared up to c sub m x to the m. That's a polynomial of degree at most m. C sub m could be 0. And you see this is a linear combination of just these powers of x. This is c0 times 1, which is x to the 0. So P sub m has a basis 1x, x squared, x cubed, up to x to the m. The dimension of Pm is m plus 1. So I have m powers of x together with the constant function 1. So the set of polynomials of degree of most m is an m plus 1 dimensional vector space. And differentiation, the differentiation operator, that you learn about in calculus, sends a polynomial of degree of most m to a polynomial of degree of most m minus 1. So in particular, I want to look at D as a linear map from polynomials of degree of most 3 to polynomials of degree of most 2. It's just differentiation, right? d of x to the k is kx to the k minus 1. Exactly what you learn in calculus. This is for k greater than or equal to 1, and d of 1 is 0. So I have P3, which has a basis 1x, x squared, and x cubed, and P2, which has a basis 1x and x squared. And the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. So these are the basis vectors for P3, 1x, x squared, x cubed. I want to write this, each of these is a linear combination of the basis for the quadratic polynomials. This is 0 times 1, 0 times x, 0 times x squared. So the matrix for this differentiation operator, for the first basis vector 1, the coordinates of where it gets sent to are 0, 0, 0. That's the first column. D of x is 1. That's 1 times 1, 0 times x, 0 times x squared. The coordinates of the basis vectors are 1, 0, 0. 2x is 0 times 1, 2 times x, 0 times x squared. So for x squared, for this basis vector, the coordinates of d of x squared are 0, 2, 0. And finally, the derivative of x cubed is 3x squared. That's 0 times 1 plus 0 times x plus 3 times x squared. We have the coordinates 0, 0, 3. That's the last column. So this is the matrix for the differentiation map from cubic to quadratic polynomials. Any questions about this? This is how you associate a matrix to a linear map. Now, we talked about already the arithmetic of matrices. You can add m by n matrices by coordinates, coordinate-wise. Remember, when you write m by n, this means m rows and n columns. So if you take m equal 2, n equal 3, we have matrices with 2 rows and 3 columns. And if I have 2 matrices of the same size, same number of rows and same number of columns, you can add them just by adding coordinates. 1 plus 7, 2 plus 8, 3 plus 9, 4 plus 10, 5 plus 11, 6 plus 12. That's addition. And you can define scalar multiplication again in the obvious way. If I have the matrix 1, 2, 3, 4, 5, 6, and I want to multiply it by 7, I multiply every coordinate by 7. And with this definition of matrix addition and scalar multiplication of a matrix, I actually get another vector space. Now, matrix multiplication is a little bit more complicated. So let's review that again. You cannot necessarily multiply matrices of the same shape. That's not the way it works. What works is when you have a matrix A, which is, let's say, an M by N matrix, and C, which is an N by P matrix. So the number of rows of A equals, sorry, the number of columns of A equals the number of rows of C. And then I can multiply them. And the way you multiply them is what's called row into column. So let's say this is matrix A, A11 up to A1N, AM1 up to AMN. And this is C11 up to C1P, CN1 up to CNP. I get some matrix, and if this is row J and column K, the number that goes into the jkth coordinate is, I take the ith row and I multiply it by the kth column in the following way. So the ith row looks like AI1 up to AIN. And here, the jth row. Okay. And here, the kth column looks like C1K down to CNK. And I just multiply coordinates and add. I get AJ1, C1K, AJ2, C2K, up to AJN, CNK. So it's easier to see when you actually work an example. So suppose I have A is a 2 by 3 matrix, and C is a 3 by 2 matrix. So let's say A is 2 by 3, 2 rows, 3 columns. I'll make it 1, 2, 3, 4, 5, 6. 2 rows, 3 columns. And C has 3 rows and 2 columns. 7, 8, 9, 10, 11, 12. And the product AC will be a 2 by 2 matrix. And you get it by multiplying row into column. So for the first row, first column, I take the first row times the first column here, and I multiply coordinates and add 7 plus 18, 7 plus 18, 25, plus 33 is 58. Over here, first row, second column, 8 plus 20 is 28, plus 36, 28 and 36 is 64. Second row, first column, let's see, 28 plus 45, 28 and 45, I think is 73, plus 66, 137 perhaps. And here, second row into second column,
Yeah, Professor.
32 plus 50 is 82, plus 72 is maybe 154. So you can check the addition, but this is the process of matrix multiplication. I mean, it's all based on how you multiply your row times a column of the same number of coordinates. This is 7 times 2 plus 9 times 0 plus 0 times 5 plus -1 times -9. That's 14 plus 0 plus 0 plus 9 is 23. So this is the simplest possible calculation with matrices. Any questions about this? So maybe let me emphasize the point why matrices are so important in linear algebra. The matrix of a linear map T from V to W with respect to bases for V and W completely determines T. So once you have the matrix for a linear map, it's easy to calculate T. So let me give an example. I'll start with an example that we had, our first example, which was the following. We had T from a two-dimensional to a three-dimensional space defined by T of x, y is x plus 3y, 2x plus 5y, 7x plus 9y. And the matrix for T with respect to the standard basis was 1, 2, 7, 3, 5, 9. So suppose that V is a vector in F2. So suppose V is the vector. So we're going to use the standard basis. So for F2, we have the basis E1, which is 1, 0, and E2, which is 0, 1. And F3 has the basis F1, which is 1, 0, 0, F2, which is 0, 1, 0, and F3, which is 0, 0, 1. And suppose we have a vector V, which is, let's say, xe1 plus ye2. That's the vector x1. And this is what T of xy is. So let's perform the following magic trick. Suppose I take the vector, the matrix M of T times, let me write this as a column vector xy. M of T is the matrix 1, 2, 7, 3, 5, 9 times xy. So this is a 3 by 2 matrix. This is a 2 by 1 matrix, 2 rows, 1 column. I can multiply them because the number of columns on the left equals the number of rows on the right. And that's going to give me a 3 by 1 matrix. When I multiply row into column, I get x plus 3y, 2x plus 5y, 7x plus 9y. It's exactly this written as a column vector instead of as a row vector. It's much better to write things as column vectors. And this is always the case. So let me just, again, review. We have a linear map T from V to W, finite dimensional vector spaces. Let's say V has a basis E1 up to En. W has a basis F1 up to Fm. And T of the vector EK is A1K W1 plus A2K W2 up to AMK WM. So T of each of these basis vectors, this is linear combination in W. The matrix of T has each of these as the column. So the kth column is A1K, A2K down to AMK. So starting from column 1. Up to column N. And so let's go through the following calculation carefully. Suppose I take a vector V in the vector space V. And suppose V is, it's going to be a linear combination x1 E1 plus x2 E2 up to xm E sub n. So T of V is going to be x1 T of E1 plus x2 T of E2 up to x sub m T of E sub n. And each T of EK, let me just use sigma notation, this is summation AIK W sub I goes from 1 up to m. So what I have here, I have, this is summation over K going from 1 up to m, right, up to n. K going from 1 up to n, x sub k T of EK. And this is summation, K goes from 1 up to n, x sub k, and T of EK is summation, I goes from 1 up to m. Let me call this J. J goes from 1 up to m, AJK WJ. And I can interchange the summation. This is summation. J goes from 1 up to m. Summation K goes from 1 up to n. AJK x sub k WJ. So T of V, so again, let's go back and make sure this is clear. I have two finite dimensional vector spaces V and W. V has dimension n, and the basis E1 up to En. W has dimension m, and the basis F1 up to Fm. And T is this linear map from V to W. How does T act on a basis vector? If I take the basis vector EK, T of EK is this linear combination of the vectors in the basis for W. And this is how I define the matrix. Now, if I take an arbitrary vector in V and I write it as a linear combination x1 up to xn of the basis vectors e1 up to xn, T of V, because T is linear, it's x1 T of e1 plus x2 T of e2 and so forth. And each of these T of e sub k's is this. And I plug it in and I rearrange, and this is what I get. So what I have is that if T of EK is summation AJKWJ, J goes from 1 up to M, and if V is summation XKEK, K goes from 1 up to N, then T of V is summation J goes from 1 up to M, summation K goes from 1 up to N, AJKXK times WJ. Now, it takes hours of work to understand what I'm doing now. I mean, it's just a couple of lines to write down, but there's a lot of mathematics embedded in the notation, and you just have to go through things step by step and look at simple examples to understand it. What happens if I take the matrix for T and multiply it by the coordinate vector x1, x2 down to x sub n? That's this matrix A11, A12 up to A1n, A21, A22 up to A2n, down to AM1, AM2, AMN. And I'm multiplying that by this vector, which is just a matrix with one column. This is M by N. This is N by 1. The result is going to be M by 1, a matrix with M coordinates. And when I do this multiplication, matrix multiplication, what I get for the first entry is summation A1K x sub K. K goes from 1 up to N, down to summation K goes from 1 up to N, A sub MK x sub K. It's exactly this. So this matrix multiplication exactly gives me, it tells me how to calculate, how to compute a linear transformation, a linear map. Let's look at another example. So a few minutes ago, I computed the linear map of differentiation from P3 to P2. And the matrix for this was 0, 0, 0, 1, 0, 0, 0, 2, 0, and 0, 0, 3. So suppose I take a polynomial f of x, I don't know, like 7 plus 2x minus 5x squared plus x cubed. So the coordinates, the basis is 1x, x squared, x cubed. The coordinates for this as a column vector would be 7, 2, minus 5, 1, or I rather write it as, this is as a row vector, as a column vector, 7, 2, minus 5, 1. So suppose I take this matrix and I multiply it are the coordinate vectors, 7, 2, minus 5, 1. So that's this matrix, 0, 1, 0, 0, times 7, 2, minus 5, 1. When I multiply row into column, I get 2 minus 5, 3. So what this says is that the derivative of the polynomial 7 plus 2x minus 5x squared plus x cubed is, here the basis is 1x and x squared, 2 minus 5x plus 3x squared. And if you remember your calculus 1, the derivative of this is this. This is the matrix for differentiating a cubic polynomial. Now, suppose I have two linear maps, S and T, linear maps from V to W, then S plus T is another linear map from V to W. And one can check that the matrix for S plus T, the matrix for the sum of two maps, is the sum of the matrices for the maps. The interesting thing is to see how matrix multiplication is related to some operation on linear maps. So suppose we have T, a linear map from U to V, and S, a linear map from V to W. So we have this picture. U goes to V under this map S, V goes to W under the map T, and then there's composition, just like you did in calculus. T composed with S is a linear map from U to W. And the big theorem about matrix multiplication in linear maps says that the matrix of the map from T composed with S is the product of the matrices, the matrix for T times the matrix of S. So this is what we call technically a miracle. That this is very beautiful relationship between matrix multiplication and composition of linear maps. And let me actually prove this. So I have three vector spaces, U, V, and W, and I need bases for them. So suppose that a basis for V is V1 up to Vn. A basis for W is W1 up to W sub m. Let's say a basis for U is U1 up to U sub P. So U has dimension P, V has dimension N, W has dimension M. And so the matrix for S, see, what are the dimensions of these spaces? V has dimension N, W has dimension M, U has dimension P. So the matrix for S is going to be matrix of what size? N by P matrix. M of T will be an M by N matrix. And when I multiply them, M of T times M of S, M by N by P, that's going to be an M by P matrix. And what we know about these matrices is that, how do we get the matrix? So suppose we let the matrix for S be equal to A, and the matrix for T to be equal to C. So this means that S of T, S goes from U to V. So I need to know what is the linear transformation S applied to the vector so I want to say what the notation looks. So T, yeah, I just wrote these letters down wrong. T is a linear map from U to V. So T is going from U to V. S is a linear map from V to W, that's S. So this composition is S composed with T. And I want to show that the matrix for S composed with T is the matrix for S composed with the matrix for T. So let me start with a little bit more space over here. I have U goes to V goes to W. S is a map from V to W. T is a map from U to V. And this composition is ST. And so U has a basis U1 up to UP. V has a basis V1 up to V sub n, and W has a basis W1 up to W sub n. So when I want to know what is the matrix for T, T of the vector U sub k is going to be some linear combination. Say R goes from 1 to n of C sub RK V sub R. So every basis vector in U is a vector in V, so it's some linear combination of the vectors in V. And every basis vector in V, say T of, say V sub R, S of the vector V sub R is going to be some linear combination of the vectors in W. M vectors in W. J goes from 1 up to M, something times Wj, and I'll call this A sub Jr. So this is T of Uk, this is S of Vr. So what is the composition? St applied to the vector U sub k. That's S of T of Uk. That's S of, and T of Uk is summation. R goes from 1 up to N, C sub Rk V sub R. By linearity, this is summation. R goes from 1 up to N, CRK S of V sub R. S of VR is this vector. So this is summation. R goes from 1 up to N, CRK. S of VR is summation. J goes from 1 up to M, AJR, WJ. By interchange summation, this is J goes from 1 up to M. Summation R goes from 1 up to N. AJR CRK times W sub J. What is this coordinate? If I multiply the matrix for S times the matrix for T, the matrix for S is A, the matrix for T is C. And when you do matrix multiplication, row into column, the j-kth coordinate of this will be summation AJR CRK. R goes from 1 up to N. That's exactly this. So the matrix for S times the matrix for T is the matrix for ST, which is the matrix whose j-kth coordinate is this. ST of UK is this linear combination of the WJs, and that's the coordinate. Now, if you can work through at home and understand the details of the proof, that's very good, but the important takeaway from this is the fact that the matrix for the composition of two linear maps is the product of the matrices for the maps. That is the fundamental fact about matrix multiplication and linear maps. And the best way to figure out what's going on is to do a lot of problems. Unfortunately, in this book, they don't have enough problems. So I might have to generate some special problems for you, but let's look at some examples. So remember when we had differentiation, D from P3 to P2, the matrix with respect to the standard basis was 0, 0, 0, 1, 0, 0, 0, 2, 0, and 0, 0, 3. I'll call this D3 because this is the derivative of a cubic polynomial. Suppose I want to find D2, which is differentiation in the simpler case from a quadratic polynomial to a linear polynomial. Remember, they teach you in calculus the derivative of a plus bx plus cx squared is b plus 2cx. So the matrix the differentiation of a quadratic polynomial, the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. So this is the matrix for differentiating a quadratic polynomial. Let's look at something which is rather cute. Suppose I take a polynomial of degree 3, I differentiate it, I get a polynomial of degree 2, I differentiate that, I get a polynomial of degree 1. So the process of going from P3 to P1, this is the second derivative. D squared. What's the derivative? What's the matrix for differentiating twice? So if you take a cubic polynomial, a plus bx plus cx squared plus dx cubed, and you differentiate it once, you get b plus 2cx plus 3dx squared. And if you differentiate it again, you get 2c plus 6 dxx. So what is the matrix for the second derivative of a cubic polynomial? It sends 1 to 0. It sends x to 0. It sends x squared. You differentiate it twice, you get 2x. So you get 2. And if you differentiate x cubed twice, you get 6x. So this is the matrix for the second derivative. Suppose I take the matrix for the third derivative. Try to squeeze it into this little space. Hope I can. Differentiating a cubic followed by differentiating the quadratic. This is the matrix 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3. Oops, let's see, so here's not good. Oh, here. Yep. Sorry. This is D3, and I want to multiply it on the right by D2. 0, 1, 0, 0, 0, 2. So this is the matrix for differentiating a quadratic. This is the matrix for differentiating a cubic. So if I differentiate a cubic, I get a quadratic. I differentiate a quadratic, I get something linear. Let's see what this is. It's 2 by 3, 3 by 4. It should be 2 by 4. When I do matrix multiplication, I get zero, 0, 2, 0. For the second row, I get 0, 0, 0, 6. And this matrix is exactly the same as this matrix. So this is just saying us that everything fits together nicely, and what you learned in calculus carries over to linear algebra. Just to make sure that you have the algebra down, suppose I take A to be the matrix 3, 5, minus 1, 4, B to be the matrix 2, 0, 1, minus 9, and do the following calculations right now. Calculate A plus B, A plus 2B, A times B, and B times A. Just do the arithmetic. A plus B, 2, 5, minus 1, 4, plus 2, 1, 0, minus 9. To add coordinates, you get 5, 6, minus 1, minus 5. Let's make this more interesting. Minus 3A plus 2B. So if I take the matrix A and I multiply it by minus 3, I multiply each coordinate by minus 3. And if I take the matrix B and I multiply each coordinate by 2, and then I add, I get minus 5, minus 13, 12, and 6 plus 12 times 18, whatever that might be. I think it's 222, but you never know. What about A times B? 3, 5, minus 1, 4, 2, 1, 0, minus 9. When I multiply, I get 6. 3 minus 45, minus 2, minus 1 minus 36 is minus 37. In BA, I multiply in the opposite order. 2, 1, 0 minus 9, 3, 5 minus 1, 4. So this is 6 minus 1 is 5. 10 plus 4 is 14. 0 plus 9 is 9. 0 minus 36. And if you compare these, you see they're different. which tells us a very important thing about matrix multiplication, right? If you have BA and BA, they're not necessarily equal. In this case, they're different. So matrix multiplication is not what is called commutative. So you need to, first of all, make sure that I did this correctly. And if I did, then see whether you got something similar. Let's look at one more example. This matrix multiplication is sort of fun. Suppose I let A be 2, 0, minus 3, 1. B be 3 by 2. So this is a 3 by 2 matrix. This is a 2 by 3 matrix. This is a 3 by 3 matrix. So you should be able to multiply A, B, C. Actually, let's make this simpler. Make this just 3 by 2. That's right. And you can do it in either order because matrix multiplication is associative. You can multiply A, B, and then C. Or you can multiply A and then BC. In fact, it's really kind of interesting to do both. Let's calculate both of these and see if they're the same. So let's take some pencil and paper. Let's see if I can do it. What is AB? AB is 2 minus 3, 7, 0, 1, minus 1, times B, which is 1 minus 1, 4, 0, 6, minus 2. So when I multiply, this is 3 by 2, 2 by 3. I'm going to get a 3 by 3 matrix. So I get 2 minus 2, 8, minus 3. 3 plus 6 is 9. Minus 12 minus 2 is minus 14. 7 minus 13. 28 plus 2, I get 30. I get that, I think. And if I multiply this by C, this is C, 0, minus 2, 1, 4, 5, 0. I get 0, 4, plus 8 is 12. I get the first row, second column, 8 minus 10 is minus 2. For the second row, I get minus 18 minus 14 is minus 32. Minus 12 plus 45, 45 minus 12 is 33. 26 and 30 is 56. And 28 minus 65, 28, 65 minus 28, 37, I think. So it looks like this is AB times C. And what about A times BC? So I have to multiply B times C. So B times C is 1 minus 1, 4, 0, 6 minus 2, times C, 0 minus 2, 1, 4, 5, 0. So this will be a 2 by 2 matrix. 0, 2 plus 4 is 6. 4 minus 5 is minus 1. Minus 12 minus 2 is minus 14. 30. So 2 by 3 times 3 by 2 is this 2 by 2 matrix. If I multiply this by A is 2, 0, minus 3, 1, 7 minus 1. So I get 2 into this. It's 12 minus 2. Minus 18 minus 14 is minus 32. 3 plus 30 is 33. 42 plus 14 is 56. Minus 7 minus 30 is minus 37. See what I get here. 28. Oh, 28 minus 37. Yeah, perfect. So if you just do all of this calculating, here I have three matrices, A, B, and C. AB times C is this. A times BC is this, and they're equal. Which means that, first of all, I was lucky today and I could multiply these two matrices correctly. And second, it's an instance of the associativity of matrix multiplication. You can't replace AB with BA, but you can associate things differently. A times BC or AB times C, and you get exactly the same matrix. Yeah. Any questions about this? This is very important in linear algebra. It's the relationship between a linear map and a matrix. All right, well, that is it for today. I will put out a homework for some more homework to make sure that you can get some practice dealing with matrices and linear maps. And it looks like it's a beautiful day, so I hope everyone can enjoy the day. I'll also be posting some office hours for the rest of the week. If anyone is interested.
Cool. I was just about to ask about, I just messaged you to ask about office hours.
Yeah. I'm going to have an office hour tonight, and I'll have office hours Thursday and Friday. And I might even have some this weekend.
Okay.
Interested. Okay. All right, take care all. That's it for today.